Okay, for our final example here, we'll consider the inductance produced by two parallel wires. So this is actually another type of transmission line. If you take two wires, in this case of equal radius, and separate them by a distance, that also creates a type of two-wire transmission line. So we would expect that the inductance of this configuration is also going to depend on length and be distributed across length, but we'll have a look at that later. So the wires have been aligned in the coordinate system as shown here. So we have two wires. Maybe we'll call this first wire wire 1 and the second one wire 2. And wire 1 is on the z-axis. And so that's very convenient because we've derived the magnetic field produced by an infinitely long wire along the z-axis. I realize that these wires are not infinitely long, but we can use the equations for infinitely long wire, which essentially is discounting fringing effects produced by a finite length wire. So here we have these two wires, and let's sketch a current. So we have a current I being carried in the plus Z direction by wire 1. And just as in the coaxial example, we have to have a return current. So that current is going to be flowing, let's say this way for wire 2. So you should take these currents that have been sketched here as a given. We could also analyze the inductance of this arrangement if the currents were parallel and in the same direction, but we're focused on the case here of this differential mode current that you see here. So now let's write out expressions for magnetic flux density so that we can arrive at magnetic flux, which is what's needed for computing inductance. So for wire 1 is fairly easy to analyze because it is along the z-axis. So we can just write verbatim what the magnetic flux density field is for that. So it's going to be mu I over 2 pi r phi hat. And again, if we use our right-hand rule, we can see that we have a magnetic flux that's a magnetic flux density that is going to be produced as you see here. And it's flowing in the phi direction according to the coordinate direction that we've coordinate axes that we've sketched on top of the wire. Now we might say that this B field is approximately equal to this because these wires are actually finite in length, and the expression that we've written there assumes that the wire was infinite in length, so this is an approximation. Before we move on to wire 2, we need to recognize that the total B field produced by wire 1 and wire 2 is going to be the superposition of the two of them. So maybe we'll just write this over here just so we don't forget that the total B field is going to be the B field produced by wire 1 and the B field produced by wire 2. And since we ultimately need to find the magnetic flux density produced by the B field here, but before we get too far, we should think about over what surface are we going to integrate to find phi. So that surface is the area over which the flux is shared between the two conductors. And so looking at this diagram, the region where the flux is going to be shared between the two conductors is actually the space between them. And a very, very convenient plane for us to choose for that would be a plane connecting the two conductors. So let's sketch that here and use a different color. So this plane between the two conductors is what's of interest here. And we can see that the B field produced by wire 1 is going to cut through that plane. And looking at wire 2, again using the right-hand rule, we're going to end up with a B field that circulates like this. This is B1 over here. And actually, for both wires, the magnetic flux density produced by both wires is upward through this green surface that we have sketched here. So let's call this the surface S. And technically, the flux is only non-zero between the two conductors where there is no conductor. So this sort of air space between the two conductors. So this is important because Writing the B field for wire 2 is going to be rather difficult because it's not along the z-axis. So the B field from wire 2 is not going to just have a phi component. It's going to also have a rho component because it's not centered on the z-axis. But because we only need to integrate the B field over S to get phi, we only care about what the B field is from each wire over S. And I think you can recognize that if we look at wire 1, the magnetic flux produced by wire 1 is completely in the vertical direction when we consider only what's happening over S. And the same thing with wire 2, is that the magnetic flux density is also in the vertical direction over S. The vertical direction here is the y direction, and so we can write our expression for the B field produced by wire 1 over S. So this is technically in the plane y equals 0. It's going to be purely y directed. So we can use the expression that we had before, mu I over 2 pi r, but now the radial distance from wire 1 is simply x, right? We don't need to use r anymore because we're evaluating the B field only over this green S area here. Now we can move on to wire 2. Let's write out the expressions for wire 2. So wire 2, we can actually now use a very, very similar formula to find the expression for by2 at y equals 0. And it's going to be equal to mu I over 2 pi. And now we need to think about the radial distance we are from wire 2. But we know that wire 2 is located at x equals d. And so the distance here is simply d minus x, right, relative to the origin. So here's our expression for by2. And to be clear, these expressions are valid over the region between a less than x less than d minus a. Right? Because we're looking at the air space between the two conductors and not over the conductors themselves. Same thing for this one. Okay, so now we have the total B field evaluated. Let's call that By total in the y equals 0 plane. We would just simply add By1 at z equals 0 plus By2 at z equals 0. Okay, so that's the total B field. Now we can carry out our surface integration in order to find total magnetic flux. So we need to draw our differential surface area elements. So let's superimpose that here. This integration can take place in Cartesian coordinates. So the width of this differential element is dx and dy, and then ds is going to point upward, which is parallel to the total B field, so that we don't have to worry about the dot product in our flux integral. So we have to integrate b dot ds over s, but this is going to be just simply b ds over s. You don't have to worry about the dot product. Now our B field is a function of x, so we can't pull B outside the integral because B is not uniform, and so we actually do need to carry out the integration in this case. So let's continue that down here. So the integration ds is dx dy, so we need to integrate x. So we're going to begin from the inner conductor, which is at x equals a, and the conductor on the left, and we will end at d minus a, again because we only care about the flux between the two conductors. Meanwhile, the other direction is dz. Sorry, when I drew this differential area element, this is dz, just looking at the coordinate system. So we're going to go from z equals 0 to, let's say, z equals L, if we assume that these two wires were the total length here was L, similar to our coaxial cable example. Now there's no variation in the Z direction, so the integration over Z you can recognize is going to be as pretty easy. Okay, let's add those two B fields together. So we have this common factor of mu I over 2 pi, and then the first term that we had on the left was 1 over x. The second term is 1 over d minus x, and then this is dz dx. Okay, the integration, like I said, over z is trivial, so phi is just equal to mu I times L over 2 pi. And now we have to integrate two separate functions. So we can integrate from x equals a to d minus a dx over x. And then the second integral is over the same limits, but it's going to be dx over d minus x. Both of these integrals are easy to handle. So let's just go ahead and evaluate those. So the first integral is just ln, or natural log, and we can evaluate that over the limits here. So this is going to be the result of the first integral. And the second integral, we can make a very simple substitution. Let's say that u equals d minus x. So, and then we are basically integrating minus du over u. So that's going to lead us to a result here of log of a over d minus a. Okay, we can simplify things a little bit because anytime we have a negative log, we can turn this into a positive log by taking the reciprocal of the argument. Right, that's just the sort of the quotient rule for logarithms. So then when we write out the expression for phi, we have mu I L times 2 over 2 pi times natural log of d minus a over a. And then these factors of 2 cancel off. Again, we only have a single turn here. We haven't wrapped these wires around anything and led to a multi-turn case. So this is actually equal to the flux linkage lambda. So we are in a position to evaluate the inductance. Inductance is defined as flux linkage divided by I. So that's going to be mu L over pi times natural log of d minus a over a. So this is our final result. We could simplify this a little bit because if we look at our diagram here, the separation distance between the wires is much larger than the wire radius. So d is much larger than a. So if d, the separation distance, is much larger than the wire radius a, then the numerator and the log argument to the log is basically d, because d overwhelms a. And we can say that L is approximately equal to mu L over pi times natural log of d over a. Again, we see that the inductance is uniformly distributed per unit length. So if we wanted to write L prime, we could just divide that out, and it's just mu over pi times ln d over a, and this would be in henries per meter. So this concludes our third and last example of inductance. Hopefully this gives you a good idea of how to compute the inductance of various different inductor geometries. And in the next video, we'll start looking at the concept of mutual inductance.